Hello, everyone. Our OCI GPU instances and RDMA superclusters have been a big hit with customers, particularly for generative AI workloads. And many Oracle apps have already introduced generative AI-driven features. With the new OCI Generative AI Service, customers now can leverage fully managed industry-leading Gen AI models to build Gen AI features for their own apps. I'm Pradeep VIncent, SVP Chief Technical Architect at OCI. In this first principles episode, we're going to talk about OCI Generative AI Service. Generative AI can create text, generate SQL queries, write code, create artwork, assist in product support. Most of these use cases have not been possible up until very recently. The Generative AI Service can host multiple customized models in a very cost-effective fashion in a dedicated OCI GPU cluster. We've been using the underlying stack to deliver generative AI functionality for many Oracle applications, including NetSuite, Fusion Apps, and healthcare. Joining me today to talk about OCI Generative AI Service, we have Igor Pushkin, architect for OCI Generative AI Service. Welcome, Igor.
Hi, Pradeep. I'm happy to be here.
So, Igor, let's start with the basics. What are these generative AI models?
Generative AI refers to a class of models that are designed to autonomously produce content, such as text, images, or even videos, based on human understandable queries. At its core, Gen AI leverages complex neural network architectures, trained on massive corpus of diverse information. They can generate novel outputs by predicting the most likely next elements based on the learned patterns. The transformer architecture marked a paradigm shift in sequence-to-sequence tasks. Transformers rely on self-attention mechanism that allows them to capture contextual relationships in the input sequences efficiently. Unlike previous models, transformers process entire input sequence simultaneously, making them highly parallelizable and efficient. Transformer models consist of a number of transformer layers stacked together and scales really well, allowing them to be trained on vast amounts of information. Here is an example of Encoder-Decoder transformer model. The encoder part of it is represented by a stack of transformer layers, converting input sequence into a set of highly contextualized embeddings. The decoder part takes input embeddings and iteratively produces output sequence of tokens, generating a single token at a time. Previously generated elements of the input of the output sequence are also fed into the decoder at each step. This way of producing content is referred to as autoregression. The transformer and the self-attention-based architecture allows generative AI systems to exhibit creativity and produce content that wasn't explicitly present in their training data.
Got it. So that makes sense. So I view Gen AI models as a massively different way to represent data and enable creative, natural conversations with the data itself. Thinking about how Oracle apps leverage Gen AI, particularly LLMs, a variety of use cases jump out, right? So like, for example, augmentation of customer support through chatbots, and analysis of vast amounts of textual data for insights and summaries, as well as end-user friendly information retrieval, summarization, and knowledge-based management, which contributes to improved decision-making process in the knowledge-intensive domains, right? So what are some of the key ingredients to leverage Gen AI in enterprise environments so that the customers can be successful?
The key to success lies in starting with the powerful base models and iteratively fine-tuning the base model using domain-specific training data. This fine-tuning process requires expertise and collaboration. With OCI Generative AI Service, customers can use the Cohere base model and fine-tuning strategy. Customers can also use other models, such as Meta's Llama 2 model.
Got it. So LLMs are known for their emergent and creative abilities that can be applied broadly, making it extremely useful right out of the box, right? But with enterprise use cases, typically there's not a lot of room for errors or incorrect creativity, if you will. How can one achieve, the accurate expectations from Gen AI implementation for enterprise use cases?
You're precisely correct. A lot of enterprises require tailored specialization and set high accuracy expectations for their AI applications. In this context, model accuracy comprises of both correctness of the output as well as its safety and responsibility. Fine-tuning LLMs with a small sample of domain-specific training data substantially improves accuracy and relevance of the output produced by LLMs. As examples, internally we took Gen AI models and fine-tuned them for specific use cases across human capital management, supply chain management, and customer experience, such as job posting generation, candidate experience summary, chat summarization, sales meeting assistant, and more. Our experiments demonstrate that the use of fine-tuning with organized data curation process can lead to real-world improvements. Additionally, with Retrieval Augmented generation, or RAG, which is supported within Generative AI Agent Service, precise data from Oracle database or OpenSearch is used in conjunction with LLM capabilities. This combination improves the accuracy even further. RAG, which is very important, also reduces hallucination by grounding generation to the relevant data extracted from the underlying system of record.
That sounds really good. That's great. So let's go over some of the most basic workflows of using OCI Gen AI Service.
Of course. At first, customers of the service formulate a task to use Gen AI in the form of LLM problem. This involves handcrafting the input prompt for the model to use along with the input data associated with the task. For instance, for a task to generate a summary of a candidate, the prompt would include an overview of the task, list areas and sections of a resume to pay attention to, and a few optional examples of how input can be represented in the output. And the candidate resume itself, which is usually appended to the prompt by a runtime system.
Got it. So you're essentially saying the prompt itself has some structured hints for the Gen AI model on areas to focus on and how to structure the output. Is that right?
Yeah, it is precisely correct. Once done, the customer runs initial evaluation of the base model by running a set of known inputs through the model and assessing the accuracy of model responses, comparing those outputs with ground truth answers. For an example, when evaluating the model on effectiveness in analyzing resumes, the customer would cycle through a set of resumes and its summaries would be compared to a handcrafted ones. This process usually incorporates prompt tuning that can significantly impact the accuracy of a base model. Fine-tuning may be required in cases when base model doesn't yield sufficiently accurate results. Fine-tuning involves gathering a small amount of training data, demonstrated desired behavior of the model in the context of a specific domain or specific use cases. Once the model successfully passes the evaluation, it is ready to deploy for inference in the form of an inference endpoint that is ready to serve live production traffic.
That's awesome. So how many custom models or fine-tuned models can a customer create with the OCI Gen AI service?
Customers can create tens or even hundreds of fine-tuned models based on business needs and the number of tasks and domains that they want to support.
So Gen AI, if I think about it, requires the use of specialized infrastructure that includes GPUs that are interconnected using cluster network to deliver ultra-high performance. OCI has an industry-leading RDMA supercluster network that delivers as low as 2 microseconds network latency. So Igor, can you talk about how OCI Gen AI Service leverages the underlying OCI GPU infrastructure?
Of course, we create a dedicated AI cluster that includes dedicated GPUs and a dedicated RDMA cluster network that can be used by those machines to communicate with each other. The GPUs used for a customer's Gen AI workload are fully isolated from other GPUs available in Gen AI service pool. Customers' inference workload and fine-tuning workloads run on this dedicated AI cluster.
So that's really good. So at OCI, we take security and privacy very seriously. So it's really good to see that we use dedicated GPUs and RDMA cluster network behind the scenes. So Igor, customer data is used to fine-tune customers' Gen AI models as well as during inferencing. So how do we protect the customer data?
First and foremost, customer data access is restricted within customer's tenancy, so that one customer's data cannot be seen by another customer. Only a customer's application can access custom models created and hosted from within that customer's tenancy. Now next, the service leverages the OCI ecosystem to deliver its data governance. It is fully integrated with OCI's identity and access management to help ensure proper authentication and authorization for customer data access. OCI's key management service stores base model keys securely. The fine-tuned customer models are stored in object store encrypted by default.
Got it. That makes a lot of sense. So we are essentially leveraging the OCI ecosystem to provide the security and governance. That's awesome. So let's go back to fine-tuning. How much training data do customers need to provide, and how resource intensive is the fine-tuning process?
Let's dive into it. Machine learning model fine-tuning has existed for a rather long time. In the past, fine-tuning involved updating most of the parameters of existing base model in order to adjust its behavior and make it more suitable for a specific application or a task. And while this method often produces high-quality results, updating all layers during fine-tuning is time-consuming and resource-intensive, resulting in much slower iterations. Additionally, serving each fine-tuned model created in such a manner requires a dedicated GPU resource that can lead to significant cost to customers. In Generative AI Service, we support this method, and it's referred to as vanilla fine-tuning. In addition to that, with OCI Gen AI Service, we use parameter-efficient fine-tuning referred to as TFU that updates only a fraction of model weights. That concept is described in 2022 publication called Few-Shot Parameter-Efficient Fine-Tuning is better and cheaper than in-context learning. This reduces training time and computational resources compared to traditional fine-tuning while also providing a good accuracy.
Got it. So this TFU fine-tuning sounds really good. So how does that work?
Fine-tuning process starts off with the base model weights and an annotated dataset. The annotated data contains of input and output pairs used during supervised training implemented in TFU. The training process yields an additional set of model weights, which are used at model serving time alongside the base model. The TFU fine-tuning is an additive parameter-efficient fine-tuning technique that inserts additional weights comprising approximately 0.01% of baseline model size.
Wait, did you just say 0.01% of the model size is updated as part of the TFU fine-tuning?
Yeah, that is precisely correct. Moreover, the weights updated are localized to just a few transformer layers during the fine-tuning process. And isolating weights to those TFU layers significantly reduces the overall training time compared to updating all layers of that large model.
Got it. That makes sense. I can imagine why that would be efficient. So can you talk about how the transformer layer works at all?
Yeah, of course. Let's dive into that. Transformer layer consists of a set of operations performed sequentially on the input data flowing through it. Specifically, it contains multi-head attention and a layer normalization, followed by a feed-forward network. Each of those operations individually are highly parallelizable in nature, leading to a very high performance of the model at inference time. The multi-head attention step can make a transformer model contextual in nature. Simply put, it looks at each element of an input sequence when computing each output value. The attention block is followed by a step combining residual connection with layer normalization. The normalization is added to normalize the distribution of intermediate layers. It enables smoother gradients, faster training, and better generalization accuracy for the overall model. During fine-tuning, a small number of weights are added to the feed-forward and the multi-head attention sections. And practically speaking, to put it in context, our configuration of TFU fine-tuning creates additional chunks of model weights of around 1 megabyte for 15 gigabyte models and 4 megabyte for 100 gigabyte models.
That's actually really small. Now I see why the TFU updates such a small amount of weights and why that can be effective. Now, in my opinion, Gen AI is still in its infancy and it is not used pervasively yet. A key to pervasive use of Gen AI is the cost efficiency of inference. This may matter less now, but I think it's going to start mattering a lot more down the road. So how do you provide cost-effective inferencing with OCI Gen AI Service?
Typically, enterprise customers have multiple use cases, as you pointed out, and domains that they want to create fine-tuned model for. Ideally, we want to host multiple of those fine-tuned models in the same private GPU cluster powered by the underlying private RDMA cluster network. This multi-tenancy drives down the cost of inferencing rather drastically.
Got it. That's really good. So generally speaking, the GPU memory is a constrained resource when it comes to Gen AI model inferencing or training for the purpose. And switching back and forth across different models incurs a lot of overhead. So how do we pack so many fine-tuned models within the same private GPU cluster?
Well, in here, the architecture of our fine-tuning models is a key to achieving cost-efficient inferencing. TFU-based fine-tuned models share most of the model weights with just a small number of weights varying across those fine-tunes. By stacking multiple specialized set of weights to a single base model, we can efficiently serve many fine-tuned models using the same set of GPUs in the underlying dedicated GPU cluster. So when we stack multiple TFU fine-tunes, we use unique identifier for each fine-tuned model. When processing an inference request against a specific fine-tuned model, only weights corresponding to that specific fine-tuned model is used. To help ensure strong privacy and security, a dedicated GPU cluster only handles fine-tuned models for the customer. As an example, let's say we have a base model with 3 fine-tuned models that are created off the same base model, and a customer creates a model endpoint for each of those 4 models. All 4 endpoints share the same cluster resources for the most efficient utilization of underlying GPUs in the dedicated GPU cluster.
I can see how this is very efficient because we have so many models and we stack them up. And then, when different inferencing request comes in, you just swap the memory for each one of those models, but it's relatively small amount of memory that you need to swap. So that's why it's very efficient, and you can actually do that. Using the same GPU cluster, you can actually share that across 4 models or 10 models or whatnot. Is that right?
Yes, that's precisely correct. And because of the size of those additional weights, we can keep a lot of those in memory at the same time, even before we start swapping.
Got it. Well, thank you, Igor. It was great having you here to talk about OCI Gen AI Service.
Thank you for having me, Pradeep. It's my pleasure.
We are excited to bring you OCI Generative AI Service. To summarize, here are some of the key takeaways. OCI Generative AI Service is a fully managed service for fine-tuning and hosting industry-leading Gen AI models. OCI Gen AI Service is engineered for enterprise customers with tight data security and privacy requirements. OCI Gen AI Service uses TFU fine-tuning technique to enable fast and efficient customization to industry-leading Gen AI models. And last but not the least, OCI Gen AI Service provides a cost-effective way to host multiple fine-tuned models by stacking many fine-tuned models belonging to the same customer in the same underlying private GPU cluster. And there's more coming. In the subsequent episode of First Principles, we're going to discuss OCI Gen AI Agent Service, including support for Retrieval Augmented Generation RAG that was recently launched in beta. The agent service makes it easier for enterprises to tap into proprietary data managed within their systems. You won't want to miss this. Thank you for joining today, and see you next time.